Okay. After understanding the basic meaning of error-free communication over a noisy channel and the meaning of error correcting codes and the requirement of the same, we are ready to describe one class of such error correcting codes in the form of block codes. So first we will restrict ourselves to the discussion of linear block codes, which is of the simplest form and that is possible. Okay, so we represented the code word as the code word having n digits, and we can represent over a row vector of consisting of n elements. Okay, Cn, and similarly our original data word or the information digits can be represented as a a row vector d of dimension k up to dk. Okay, so these are the tuples. N tuple vector and k tuple vector are represented by the code word and data word respectively. Okay, so for a general case of linear block codes, as we have seen that block codes are nothing but we will wait for k data digits to be accumulated, and then we try to encode as a code word, as a n tuple code word. Okay, so for the general case, all the n digits C are formed by the linear combinations of k data digits. So the linearity term indicates that the linear block codes in general, I can say that is nothing but C is formed by all the linear combinations of k data digits. C is equal to linear combinations of di's. Okay, so combination in the sense we'll have to make additions of all these data digits. The addition in binary is your XOR addition or modulo to addition. Okay, so remember the addition here is can be thought of XOR operation or modulo to addition. So in case of modulo to addition, both addition and subtraction have the same meaning. Okay, will result in the same binary digit. All right. So in a special case, if I say I call such codes as systematic codes, are these are the one of the special types of linear block codes where all your code words first k data digits are equivalent to the code words, where C1 is equal to D1, C2 is equal to D2, so on up to Cn. Sorry, there are k data digits, and I can say that Ck is equal to Dk. Okay, obviously we have known that n is greater than k. Okay, so all the data words or the digits in the data words are nothing but the code words, but rest of the digits in the code word, say from Ck plus 1, from Ck plus 1 onwards, these are found by linear combinations of the data digits. So I can say that these are the linear combinations. So it's a modulo 2 addition, H12 D2 up to H1k dk, right? And similarly Ck plus 2 would be H12 D1 XORed with H. So since this is a second row, so you can say this as H21 D1, and this is H22 D2 XORed up to H2k dk, and this runs for up to Cn, since there are n, say a code word is an n tuple data vector, so Cn can go up to hm1 d1 XORed with hm2 d2 and so on up to hmk dk. So the subscript m represents where m is nothing but n minus k, where it represents, m represents check digits or redundant digits. Okay, so up to k it's everything is fine. We are adding extra digits or extra redundancy digits, we call them as check digits in order to compensate for, or in order to form an error correcting code. Okay, that's the reason there are m rows of these are the coefficients where h, I can say this is hij, okay, are nothing but these are coefficients. Okay, these are coefficients, and of course I varies from 1 to m, and j also varies from 1 to m. Sorry, j varies from 1 to k. Okay, so and hence we can form systematic codes. I repeat, systematic codes are those codes where the first k digits in code word are identical to the data digits themselves, and rest of m check digits are formed by the linear combinations of all the data digits involved. Or in matrix form, I can represent this as, or C can be represented as simply D multiplied by a matrix which is formed by the coefficient matrix which is called as G, where okay, this is one of the important form of representing a systematic code. Okay, where G is called as generator matrix. Okay, because this generates the code words based on the data input. So G is represented as a matrix where the first form of matrix is an identity matrix, and it goes up to to 1. Okay, so this is augmented by, this is an augmented matrix by another matrix which is formed by the coefficients h11, h21 up to hm1, h12, h22 and so on up to hm2. Okay, and this runs up to, as we know, up to h1k, h2k and up to hmk. Okay, so this is called as a generator matrix. This can also be represented in a shorthand notation as, or the matrix G can be represented as the first matrix is ik, which is augmented by, okay, I can say this is augmented by a matrix which is found by all the coefficients, and we call that as P, which is of the order p k cross m. So this is k cross k, and hence this is a shorthand notation of representing the generator matrix. Okay, so the order of generator matrix, obviously this is not the product of these two matrix, so generator matrix will have the order of k cross n. Okay, so this is the size of the generator matrix. Okay, so for systematic codes we can partition this generator matrix as an identity matrix of size k, and a matrix P is called as, where P is called as parity matrix, okay, which comprises of all the coefficients. Okay, so when we take in a specific cases this will be more clear, but you should know the general form of it as well. Alright. Okay, so we have the representation, the shorthand notation as, so therefore what we have with us is C is represented as D times G, right? So G in the shorthand notation we have represented it as D as I K P. This is an augmented matrix. Then I can take this D inside. We can pull this D inside as a a product of these two matrices. So I can represent this as I know that multiplication of any vector with respect to the identity matrix itself is the vector itself. So this is D, and this multiplication will result in D times P. Okay, so which is nothing but I can represent it as D C P. Okay, so this is the resulted code word. Okay, so this also an important form that we will be utilizing in a further point of the course. Okay, where this CP is actually called as checksum or parity bits. It's a vector, right? Because D is a vector, P is a matrix, multiplication of these two will give me a vector itself, so that this is a row vector which will consist of all the checksum bits or parity bits is nothing but D times P. Okay, so knowing the data digits, with the information of data digits we can calculate the check digits, okay, and consequently the code word C. Okay, so the weight of code word, so remember we have a parameter called as weight of a code word, of any code word C in general, is nothing but the number of ones in the code word. Okay, this is used extensively in the course as weight of a code word. So just we have to calculate the number of ones in the code word, and that would be the weight, and the Hamming distance between any code words, between any two code words, okay, say CA and CB, okay, is nothing but be represented as distance between CA and CB is nothing but the weight of CA XORed with CB. Okay, so if you want to find out the number of bits in which two code words differ. That's what is the definition of Hamming distance, as we have seen earlier, right? So if you want to find out the Hamming distance between any two code words, we have to just take the XOR of those two code words and the number of ones in the resultant of the XOR of these two code words would give us the Hamming distance, okay, which is the weight of the XOR of those two code words. Let us take one simple example to describe this before we move forward to the linear block codes in general. So remember, this is the case with systematic codes. Okay, say for example, okay, consider say a 6,3 code with, of course, generator matrix should be given to you. So with the generator matrix, which is represented as 1 0 0 0 1 0, this is of the size of 3, and 1 0 1 0 1 1 1 1 0. Okay, so this is of the form I K. Okay, so this is of the form which is nothing but this is a parity matrix. What we need to find out here is that we are supposed to find the possible data words and corresponding code words. Okay, and we can also find out the number of errors that this code can correct. Okay, so these two quantities if you want to find out, this is very simple task. Okay, so all we need to do is the code word, as we know, is simply D times G. Okay, this is simply D times G, so that we know since it's a 3-bit data word, because as we see K is 3 here, since N is 6 and K is 3, this is a 6,3 block code. So there are 3 digits by the message digits or the data digits. So there are 8 combinations that are possible, so that the data word and corresponding code word can be tabulated like this. Say for all the combinations, say 111 110 111 110 101 100 011 010 001 and 000. So there are 8 possible data words, and corresponding code word is just multiplication of this data word into generator matrix G, right? So for 111 I can simply without performing actual matrix multiplication, I can say that 111 times the entire matrix is is first, since first column is just 100, this will be simply 1, and for again for 1 it will be 1 here, and 1 is another bit in the code word, and for the other 3 digits in the code word, so 1 times 1 plus 1 times 1, which we know that XOR of that operation is 0, and similarly for the next digit is 0, similarly for the next digit is 0, and hence this can be continued for other combinations. So 110, for 110 similarly this is 1 times 1, then 1 times 0, then 0 times 1 is 0. So and hence, so the first 3 digits would be same. Then next multiplication is with respect to the parity matrix. This would result in 1, and next is 1 1 0. So 1 times 1 0 is 0, 1 times 1 is 1, plus 0 times 1 is 0, and hence this would be 1 as well. And for the last combination, since it is 0, 1 times 1 plus 1 times 1, which is binary addition or XOR addition, would result in 0. Similarly, you can verify that for all other combinations, we would get this as 1 0 1 0 1 1 1 0 0 1 0 1 0 1 1, and this would be 1 0 1, and this would be 0 1 0 0 1 1 0 0 1 and 1 1 0, and for all zeros you get all zeros, right? So this follows a systematic code, as I have seen, we have seen in a generic case. The first k digits, first 3 digits are nothing but the data digits, followed by the parity or checksum digits, which are formulated by linear combination of the data digits that have been fed to the generator matrix. All right. So note that the distance between any 2 code words, if you can find out the Hamming distance, or you can say in fact any distance between the 2 code words taken at random is nothing but 3. You can check that. Okay, so you can take pick 2 code words and take modulo 2 addition of those two code words and find the number of ones in the result of the modulo 2 additions. That would give you 3. So this implies that if the distance between any 2 code words is 3, then from the formula that we know that the Hamming distance is related to the number of error correcting codes is t. With that, I can say that t, which is the number of errors that this code can correct, is t is equal to 1. Okay, so this is single bit error correcting code. In fact, we can implement this with basic your XOR operations, where D1, D2, D3 can be taken directly to C1, C2, C3, which are equivalent, and rest the code the digits in the code word from C4 to C6 are linear combinations or simply XOR operations of the data digits themselves. Okay. However, we will not try to draw the structure which can be easily drawn. Alright, so this is about systematic codes. Next, we'll move on to the most important and most generic type of codes, which is called as linear codes. Okay, a block code, as we have seen, is a linear block code. If for a block code, of course these are block codes, a class of block codes. A block code is a linear block code, if for every pair of code words from the block code, say you have got a block code and you have got the table of say all these block codes. Say for any 2 code words, say I'll say CA and CB in general. If C and CB are any 2 code words in the block code, then the modulo 2 addition, or simply the binary addition of these two code word is also a code word. Then such codes are called as linear block codes. Okay, so for this reason, we must have two properties, okay, which is nothing but the properties, I can say, of LBC. Okay, the first important property is that must have linear codes, must have all 0 code word. Okay, so in the sense the code word would be simply running trails of 0 zeros. Okay, so second important property based on this statement of linear block code, the minimum distance, the minimum having distance, of course, the minimum distance which is represented as d min is equivalent to the minimum weight. Okay, so we'll understand this property once we take in a specific cases, but these two are the important properties based on the nature of the construction of the linear block codes. Okay, this how we can see, but thing is we should look into the decoding part as well, how the receiver tries to decode when it receives the code words at its end. Okay, so let's consider some code word properties. Let's use them and try to use them for a purpose of decoding. Okay, so from the fact that modulo 2 sum of any sequence with itself, what would this result in? So if I take any sequence or any code word, and if I take modulo 2 sum with itself, this would result in 0, correct, because of the property of modulo 2 sum, right? So this implies that I can take the modulo 2 sum of the parity checksum bits themselves, where CP XOR CP should result in 0. But we have seen that we have represented CP as D times P. If you check back, that we have represented the block codes in general, where CP was represented as simply the product of data digits and the parity matrix itself. So with that known fact, we can write this as, so this implies I can write this as D times P. We can say these are the two matrices, so I can take the inner product of these two. Okay, so XOR with CP should result in 0, or I can rewrite this in terms of the matrix form, where the first I can take it as the product of two matrices, where this is D and this is CP, can be multiplied with a matrix P and then with the identity matrix IM. See that left hand side is same, where if I take the product of these two composite matrices, so this will be D times P, right, plus CP times IM, which is CP itself, right? We have not done anything great. We have just rearranged these composite matrices of the form of modulo 2 addition. So obviously even this product should result in 0. Okay, so remember that this dCp we have also represented as d dot p. So if you go back, we have represented that d dot p as cp. Based on that fact, we are just rewriting this product of two matrices. Okay, where IM represents the identity matrix. Of course, this should be of the order m, because CP is of the order 1 cross m, where CP is of the order, sorry, so this is of the order 1 cross m. So this is a row vector, correct? Since there are p checksums, or in case of the parameter that we have told as m, where m is nothing but n minus k. That's the reason this identity matrix is of the size m. Okay, all right. So this implies that this results in an important form of the matrix, where if I call this matrix as simply as C, and this matrix simply as, say, a matrix H with transpose, I can represent this with the shorthand notation as simply C times HT, which is equal to 0. Okay, so note this is an important relation that we are going to use while we are decoding. Okay, so this is an important expression that will serve as a good reference. Okay, where H transpose that we are represented as PIM, or I can simply say take the transpose of this and represent as PIM, is called as, okay, of course this is, and take transpose, this will also be a transpose. The identity matrix will have transpose which is identical to its original matrix itself. Okay, so this matrix H is known as parity check matrix. Okay, so every code word, since this is a generic expression for any code word, where if I take modulo to sum of any two code words would be 0, and it should satisfy this expression. So the above expression, okay, the above equation must be satisfied by every code word. I cannot say any, by every code word. Okay, let us take the case with the receiver now. Okay, at the receiver, suppose the receiver receives a code, or say simply I can say this is a word, say R. Okay, so if there is no noise in the channel, then obviously we can find out what is actually transmitted. R would be simply equal to C, right? So we can uniquely determine what is the data or the information digits that is transmitted. So due to the noise in the channel, again, so R whatever is received by the receiver, okay, due to noise, I can say the received word will should supposed to be of equivalent to C, but with certain error, I can say this as error vector as E, which is added in the channel itself. Alright, since it's bits, I can take I'm sorry, as the modulo 2 addition of the code word and a error word. Okay, we can say that where E is called as error vector. Okay. Suppose the sorry, if the transmitted code word let us say that if the transmitted code word is CI for some I, okay, and the channel produces an error with channel noise EI, then the received word can be represented as CI XOR EI. Okay, then we have said that if we say that the received code word is RI, so this is also a form of a code word. So we have said that every code word should must satisfy this equation C times H transpose equal to 0. So this but since this C is not the C which is transmitted by the transmitter, obviously if you take the product of, so then I can say then obviously the product of RI times HT would not be equal to 0 because of noise, due to noise. If it was exactly the code word, then definitely this should have been this would have satisfied our equation even at the receiver. But Ri, we have, the non-zero quantity, we call it as some matrix S which is resulted in the product of these two vectors, where S is called as syndrome. Okay, so syndrome is a vector which is a non-zero vector when we take the inner product of the received vector with the parity check matrix, then that would result in a syndrome. Okay, so since R is nothing but CI XORed with EI, since that is what is transmitted from the transmitter and corrupted by the noise in the channel, so we can represent this as CI times HT XORed with EI times HT, and we know that the first part of this product is 0 and the syndrome can be represented as, the syndrome vector can be represented as EI, the error vector, times HT. Okay, fine. So upon receiving R, we can compute the syndrome vector S. Okay, by doing this operation, by receiving R, we'll try to take the inner product with generator, the parity check matrix, and we can calculate S. So but knowing S, we see that it feels that we can also find out what is the exact error that is caused in the channel, which we can try to eliminate in the received vector and try to decode or demodulate perfectly. But unfortunately, with the property of linear block code, what is the property of linear block code? One of the important properties that any combination of two vectors can generate another code word. In the sense that any two code words in a linear block code can generate a code word which is also a perfect code word that exists in the transmission. So because of the property of LBC, this syndrome vector S could also be true for any vector, where if if I say rj is a received vector, and if I say this is cj XORed with ej, even this s could also be a combination of this rj times ht, and since this is cj XORed with ej times ht, and this would result in the same syndrome but with some different error ej. Therefore this seems that the knowledge of syndrome S does not allow to uniquely determine EI. Okay, so this EI could also represent, I mean, if we know EI, it feels that we can, I mean, by knowing the knowledge of syndrome, we can find out EI, and it feels that we can find out what is the code that is transmitted. But sometimes it may so happen that due to the property of block code, this error, with the knowledge of error or the syndrome per se, we cannot uniquely determine, it will not give a unique solution of the error which has occurred in the channel. Okay, so how many code words are there? Because of since there are 2 power k code words possible, okay, then we can, in general, I can say that this syndrome can be in general be written as E times ht. So for any E, for plenty of values of E, for many combinations of E, we can there is a possibility of getting the same syndrome. Okay, so and hence just by the knowledge of syndrome we cannot able to decode properly. Then how do we resolve this? Okay, we must come to a point where we should design a receiver with a proper decision criterion. Okay, so the decision criterion at the receiver is implemented, which is known as maximum likelihood rule or maximum likelihood estimation, which we will be exploring much in the communication system 2 course. But what we can define at this point is, this means that all we need to do is we decide in favor of, once we receive the vector r at the receiver, we decide in favor of that code word C for which the vector r is most likely to be received. In other words, mathematically, the probability of the vector r which is received, given that the code Ci is transmitted, and we will map it onto that code word, if this condition probability is greater than, or I can say strictly greater than, I cannot say equal, if it is strictly greater than with the probability of receiving the word r, given that any other code word ck is transmitted. Okay, so this is for all k obviously not equal to I. Okay, although it seems to be a complicated decision rule, but for the binary symmetric channel, where we have seen that bit 0 is transmitted, and there is a possibility of flipping it as 1, or receiving it as 0 itself, such binary symmetric channel, the decision criteria would be simple. For a binary symmetric channel, the rule is very simple, where if I say the Hamming distance between, if I say the Hamming distance between, let's say that as Hamming distance between, say, vector r and Ci, if I say this as d, Okay, it's simply D, it's not a vector, otherwise it would represent the data digits. Say if it is D, then I can say that the channel noise causes errors in D digits. Okay, and if the channel noise corrupts D digits, then we can say that probability, the conditional probability of receiving R given Ci simply obeys this rule, where probability of error, so probability of error is nothing but probability of sending one, receiving one if 0 was sent, or which is also equal to probability of receiving 0 if 1 was sent. Okay, that's a binary symmetric channel. So PE times D, because there are the errors in the number of digits as D, and obviously 1 minus P are received correctly, that will occur with n minus D terms. Alright, so this can be rearranged as 1 minus PE times n. Okay, D is this 1 minus PE can be pulled over, which can be written as PE over 1 minus PE whole power D. Okay, say for if this PE is less than half or 0.5, holds for a reasonable channel, then P of R given Si is a monotonically decreasing function of D. Okay, then this P probability R given Ci is a monotonically decreasing function of D, because of the fact that PE 1 P over 1 minus PE is obviously lesser than 1. Okay, as the number of errors increase, this condition probability keep on decreasing. Okay, hence to maximize this condition probability, we must choose that Ci which is closest to R. Okay, and hence the decision criteria would be such that we will implement this once we take specific example. So this implies that to maximize PR given Ci, we must choose that Ci which is closest to R. Okay, so that is, we must choose the error vector with the smallest number of ones, since we know that the distance between two codes is is also weight, using the second property of linear block codes. This means that we must choose an error vector, or we must choose the error vector E with the smallest number of ones. Okay, we must choose error vector E with minimum weight or number of ones. Okay, so a vector with E with E as the smallest number of ones is called the minimum weight vector. So this is nothing but the E vector with minimum weight is represented as E minimum. Okay, so therefore this minimum weight error vector will be used to correct the error. Okay, so therefore vector R, sorry, the code word that is decoded as C upon receiving R XOR with that error vector with minimum weight. This would be the decision criteria. Okay, we'll take specific cases in the next class and try to understand the generic meaning of all these explanations. Okay, thank you.